I continue talks on homogenization theory, but, well, classical homogenization problems, but these problems will not be purely periodic problems. So they are locally periodics. And, well, on a domain. I'm going to talk about some problem, say a Dirichlet problem on, for example, bounded domain with smooth boundary, with, say, Dirichlet boundary conditions. Okay, Dirichlet boundary conditions. And it is well known from classical theory that the solution to this problem converges strongly in L2 to the solution of a similar problem, but with slowly varying coefficients. You see here A epsilon, it is a function that depends on a parameter. And when the parameter, well, we have a family of problems, and usually in applications, these problems describe some physical processes in highly heterogeneous medium, and the smaller epsilon, the more heterogeneous medium is, the underlying heterogeneous media is. So we're trying to approximate some process in highly heterogeneous. It's more difficult process than in homogeneous medium. We're trying to approximate it by some more simple process. Okay, that's the background. So it is well known that U epsilon converges in L2 strongly. That has been known from the early 70s, I suppose. More recent results for the first place of, I suppose, Zhikov and Pastukhova, 2005, and Grisot, 2004 and 2006. So they proved that for purely periodic problem, for a problem where the coefficients, purely periodic problems, where the coefficients depend only on the fast variable. So what's the fast variable? The variable x over epsilon. The function a is one periodic. So this function of x is epsilon periodic, and when epsilon is slow, this function oscillates with period epsilon, rapidly oscillates. So for this problem, they proved that as in the whole space case, which have been mentioned before several times, they proved that the function u epsilon converges to u naught, in fact, uniformly in the right-hand side. So the resolvent of the initial problem converges to the resolvent of the limiting problem in the operator topology. What is more, they found the rate of approximation, which is epsilon to the power of 1, and this was the result of Grisot. Again, for purely periodic problem. So rapidly oscillating function. Here's the period epsilon. And purely periodic problems have been thoroughly studied during the past 20 years. And this is not so for non-periodic problems. The simplest one, I think that the simplest one is obtained as follows. We take periodic rapidly oscillating function and allow its amplitude to slowly vary, to slowly change in the space. So something like this. Rapidly oscillating function with slowly varying amplitude. So we arrive at a problem with locally periodic coefficients. Locally periodic problems. The coefficients of these problems depend on the fast variable, x over epsilon as before. This is periodic, maybe non-smooth variable, and the slow variable x, which is smooth. So the function a is, in some sense, smooth in the first variable. Okay, and my aim now is to carry over those results for purely periodic problems to locally periodic problems. And that's what I'm going to talk about. Problem formulation. We fix a domain, omega, in RD, which is Elliptic domain, may be unbounded. We don't require it. And to fix boundary conditions, we introduce a scale of spaces curly WQ, curly WQ1. So this is a subspace of the ordinary suballoy space WQ1, which contains all smooth, compactly supported functions, right? So this will be the domain of the operator. The extreme cases are Dirichlet and Neumann boundary conditions, and the other cases are the mixed boundary conditions. So we fix P, which is greater than 1 and is finite, and consider an operator A epsilon from the curly WP1 to curly WP minus 1, which is the dual of WP plus 1, where P plus is the Helder conjugate of P. So this is the operator is given by this form, by this formula. This is a matrix operator with locally periodic coefficients. So second order linear differential operator. The coefficients are described by the function a. So we assume that a is periodic in the fast variable in x over epsilon, and Lipschitz in the first variable, in the variable x. So the initial operator the initial operator that's the initial operator. This is bounded operator because the function a is uniformly bounded. So this is a bounded operator between these two spaces. And we assume that there is a mu on the complex plane so that the resolvent of this operator is also bounded between the second and the first spaces. So that's our assumption 1. That's the assumption 1. So there exists mu on the complex plane so that the resolvent at the point mu is uniformly bounded with respect to the parameter WP minus 1 to W curly WP 1, uniformly bounded. For sufficiently small epsilon. Okay, so for epsilon less than or equal to some positive epsilon 0, epsilon naught. This is quite natural assumption because if we want the resolvent to converge even in the weak operator topology, then this family has to be uniformly bounded. So we assume that it is bounded. Now I'm listing all the assumptions I need, and next I will provide some examples that satisfy these assumptions. So now only the assumptions comes. As in the purely periodic settings, the resolvent converges to the resolvent of a similar operator, to the so-called effective operator, which of a similar form, and the effective operator is acting between the same spaces. This is a very well-known result, very well-known formulas. So the effective operator the effective operator between the same spaces. And the effective coefficients is given by this formula. We have seen this formula today twice, I think, but there is a difference. Now, the right-hand side depends on a parameter epsilon. So epsilon, the slope variable, now is a new parameter. And therefore, the effective coefficient, sorry, x, sorry, yes. And so the effective coefficient A now depends on x. So it is no longer a constant function. What is n? As in the purely periodic case, n is the solution to the so-called cell problem. So the cell problem now it depends on x. That's the only difference. But since I haven't assumed that the initial operator is elliptic, now I have to assume that there is a solution. In application, this would be an elliptic problem, so there will be a unique solution. Now I assume that there is a solution which is Lipschitz in the first variable, Lipschitz in the parameter x, with values in the Sobolev space WP1 in the periodic Sobolev space, with the same p as for the initial operator. So that's our assumption number 2. Assumption number 2. The solution to the cell problem is Lipschitz in the slope variable. That's the assumption number 2. Okay. Then the derivative of n with respect to the first variable with respect to the second variable is also Lipschitz in the first variable, right? So it's in WP1 in the second variable. So let's go back to the definition of the effective operator. Then the effective coefficient is also Lipschitz in the parameter x, in the slow variable x, because a is Lipschitz and the other function is also Lipschitz. So the effective operator is now, well, it's now very nice as well. It is second order differential operator with Lipschitz coefficients. We assume, and that's the assumption number 3, that that the resolvent is sufficiently regular. So that's the last assumption number 3. We assume that the resolvent of the effective operator is bounded from LP with the same P as before to the so-called Lipschitz-Besov space lambda P1. So what is lambda P1? Oh, sorry. 1 plus S. There is a positive S, so that the solution to the effective problem is sufficiently regular. What does it mean? Lambda P 1 plus S. That is the space of all the functions in omega on omega in WP1 in the sublet space WP1. Here it's comma. We have just P and P plus, nothing else for now. Lambda P 1 plus S is the space of all functions in WP1 on omega, so that the LP modulus of continuity of the gradient of U at point T is majorized by T to the power of S times some constant. For S equal to 1, this is just the ordinary sublet space WP2. And for S between 0 and 1, then this is the Besov space B P infinity 1 plus S. Okay, so that's our last assumption. It is well known that even the resolvent converges in L2, its derivative does not converge even weakly in L2. So we have to introduce a corrector S as in the purely periodic case, of course. So now, what is a character now? This is just a regularized classical character. We take the solution to the cell problem, the function n, multiplied by the derivative of the solution to the effective problem, and then we modify it in the slope variable. So this is just a regularized and modified classical character. And this is a bounded operator from LP to the ordinary Sobolev space WP1. What we have proved. The theorem 1. The first theorem, suppose that or the assumptions hold. Then the resolvent to the initial problem converges to the resolvent of the effective problem. There should be F here. There should be F here. Converges in the operator norm on LP. There is no prime here as well. At the rate epsilon to the power of S over P. And there is no convergence in the Sobolev space, but the resolvent of the initial problem at the point mu, which we have fixed in the assumption 1, the resolvent can be approximated as usual by the sum of the resolvent of the effective problem and the character I have introduced on the previous slide. And the rate of approximation is the same as before. So epsilon to the power of S over P. That's not sharp. That's not sharp, and to improve the rate, we can improve the rate. So the rate depends on the regularity properties of the effective problem, but we can improve the rate if the adjoint effective problem is regular as well. So the initial operator is not self-adjoint, but its adjoint is of the same form as the initial operator. So we can introduce all the objects for the adjoint operator as for the initial operator, and introduce all the assumptions for the adjoint of the effective operator as well. Then, if all the assumptions for the initial operator and all the assumptions for the adjoint operator, similar assumptions for the adjoint operator, hold, then the first approximation, we have an improvement in the first approximation. The rate is now S over P, epsilon to the power of S over P plus S plus over P plus. So what's P plus is the conjugate, Hölder conjugate of P as before, and S plus is just a positive question. S plus is a parameter from the assumption number 3 for the adjoint. So, for example, if S plus is equal to S, then the rate is epsilon to the S. That's the results. And now I'm going to Now I'm going to provide some examples. Okay, strongly elliptic operators are those examples. Let gamma k be part of the boundary of the domain, or the empty set. Then we introduce the spaces WQ1, the scale of subalef spaces WQ1, which are just the direct sum of the subalef spaces of functions that vanish near the set gamma k. So we have the Dirichlet boundary condition on gamma k and Neumann on the complement. And okay, this is the operator. It is of the same form as before, and this is a matrix operator. So it acts on vector on subalef space of vector values functions, and different components of these functions may satisfy different boundary conditions. Okay, so and we start with the exponent p equal to 2 as usual. So we start from the Hilbert space W, the curly W21. Okay, and we assume that these operators are uniformly elliptic. Uniformly, I mean uniformly with respect to the small parameter epsilon. So there is so for sufficiently small epsilon, this Gardner type inequality holds with constants independent on epsilon. So these operators are uniformly bounded and uniformly elliptic. So there is a sector on the complex plane. Sector on the complex plane, so that for any mu outside that sector, the resolvent of these operators at mu is bounded. For p equal to 2, we start from the exponent p equal to 2. So we take mu somewhere here, and the resolvent at this point is bounded. Then by the Schneiberg theorem, there is a neighborhood of the point 2, so that the resolvent is in fact is bounded for any p in this neighborhood. But this neighborhood depends on mu. Oh, that's easy. Schneiberg. If we have a bounded operator between between scales of some spaces, then and which have an inverse at some point, then it has an inverse for some neighborhood. And moreover, we can, in fact, we can find p mu explicitly. We can find p mu explicitly. Okay, I claim that, and that's very easy, that then these resolvents are continuous for any p in the union of these sets. Not only for p in the set p mu, but in the union. And that's very easy to prove, so maybe I prove it now. Suppose that P, so we have two parameters, nu and mu, outside the sector S. And suppose that P is greater than P nu, greater than 2 and less than P nu. Then the resolvent at mu is bounded for this P, right? So it's bounded from WP minus 1 to WP 1. And now I want to prove that, in fact, the resolvent of A epsilon at mu is also bounded between these two spaces. Then we that's in fact our assumption 1. That's the assumption 1. The resolvent of the initial operator is uniformly bounded for any P in the set capital P. That's the assumption number 1. What about the assumption 2? If the initial operator is uniformly elliptic, then by the two-scale convergence or by any other means, one can prove that the operator of the cell problem is also uniformly elliptic with better ellipticity constants. So, in fact, this is the operator of the cell problem. You see here x is fixed, and the operator x on the fast variable only, on the periodic variable only, and then this operator is uniformly elliptic as well, and by the Schneeberg theorem, again, there is some neighborhood of the point 2, and in fact, this neighborhood may be larger than the set capital P, but in particular, the inverse of the cell problem operator is bounded for any P in the set capital P. And then the solution to the cell problem, okay, it satisfies the assumption 2 for any P in the set capital 2. So the second assumption, our second assumption, is also satisfied. What about the effective operator? The effective operator is a nice operator with Lipschitz coefficients. So it is bounded between the Sobolev spaces curly WP1 and curly WP minus 1 for any, in fact for any P larger than 1. So what about additional regularity? What about the additional regularity in the assumption 3? Okay, this regularity depends on the boundary conditions. So the assumption number 3 for nice boundary conditions for Dirichlet or Neumann boundary conditions, Okay, we have if omega is a Lipschitz and convex domain, and the operator is a scalar operator. So n equal to 1, a epsilon is scalar. And scalar. So if the boundary is Lipschitz and convex, and the operator is a scalar operator, then we have S equal to S plus and P equal to 2. Then the assumption for the effective operator and for the adjoint, which is of the same class, then they are then these the inverses of these operators are continuous from L2 to W2 2. Oh, sorry. That's what I mean. If the domain is, for example, C11, so the derivative is Lipschitz. This condition can be weakened, but if the domain is C11 and the operator is matrix operator, then of course S is equal to S plus is equal to 1, and P is any number in the set capital P. So this is the union of the neighborhoods. In the other cases, okay, if the boundary conditions are the mixed ones, so the mixed Dirichlet-Neumann boundary conditions, then if the domain is C11 and gamma k, which I introduced before, so if the parts of the boundary where we impose the Dirichlet boundary conditions, if those parts are C11 submanifolds with edge, then and the effective operator is self-adjoint, is formally self-adjoint. So the effective matrix is self-adjoint, and the operator, it may be matrix as well. There is no restriction here. Then S is equal to S plus is equal to 1/2 and P is equal to 2. So the resolvent of the effective operator is bounded from L2 to lambda 2 3/2, and this is sharp in the exponent S. So this result cannot be improved. 97. Sorry. Okay, that's the examples to illustrate the results. The last result I want to mention is about nice boundary conditions. So either Dirichlet or Neumann boundary conditions, and so we assume all the previous assumptions. So the operator is uniformly elliptic as before, and in addition, we assume that the function a is uniformly bounded in the slope variable and in VMO class in the fast variable. So then all the assumptions for the initial operator as well as for the adjoint operator are satisfied for any p greater than 1 and s equal to s plus equal to 1. So that's another example.